6.6, another jump in our chapter, and this time it's to vectors. Yes, we did see some vectors in geometry, and just like in geometry, vectors have both magnitude and direction, so our size and our direction. We also have what we talk about scalar quantities or scalars that just have magnitude, but they don't have a direction to them. So running through some things here, vectors are equal if they have the same magnitude and the same direction. You have a scalar multiplication, so K is usually what we symbolize with our scalars, and V is usually what we're going to use for our vector. So if you see K times V or KV beside each other, basically what you're taking is the magnitude or the scalar, that number, times the magnitude of the vector, okay, the size of the vector. If K is greater than 0, it goes in the same direction. If K is negative, it means we're kind of reversing the direction of it. So that's one thing that we're working with there. Okay, here I'm going to give you a couple different things. Number one, I want you to recognize when there's these double lines on something, okay, that means that they want the magnitude. They want us to find the size. The other thing that's very different than in geometry, we're going to add an I and a j to our vectors. Our I is the horizontal component, okay, that goes along here, and our j is going to be the vertical component. And basically, when you think of these I and j, they're simply going to stay with our numbers to remind us which one's the horizontal, which one's the vertical. One reason I'm not real keen on this being in the same chapter is we just finished some complex work, and we use I, of course, with complex numbers, with the imaginary. But this I is different. This I is just a horizontal component. This j is a vertical component. And the I is going to sit on the first term, the j on the second term, basically. Okay, so just keep that in mind, that that's what the I and the j kind of are doing here. And I forgot to arrow there when I went to move the page. All right, so representing vectors in rectangular coordinates. What we're going to do basically, if you go from 0, 0 to AB, that means you've moved horizontally A, so A times I, that I just holding our horizontal movement. From 0 to B would be vertical, B spot, so BJ, okay? So V is our vector, and A, or whatever horizontal movement stays with the I, whatever vertical movement stays with the J. Size, magnitude, okay? The magnitude is the square root of a squared plus b squared, which looks like our r that we've been doing since we started polar coordinates, okay? So the math involved will look similar to that, okay? So let's say you have negative 3i plus 5j down here. So if you think about where is this going, well, I went to the left, negative 3. I went positive 5. And that's what my I and the j keep us horizontal and vertical. And I want to find its magnitude, its size. How far did it go from 0? It looks like our r. Okay, this is my vector here. That's what happened there. So I want its size. So the magnitude of v is going to be the square root of my negative 3 squared plus my 5 squared. This math should look very familiar to what we've already done this chapter. Negative 3 squared is 9, 5 squared is 25. 9 plus 25 is the square root of 34. If it simplifies, simplify it. If not, leave it. There's my magnitude for this particular vector, okay? Magnitude looks like our r. That's one of the key things to remember. All right, representing vectors in rectangular coordinates. To be honest, it's just including that I and that j. Now, one thing that I do want to run through on this example, if you start with an initial point, so here's where my vector starts, here's where my vector ends, so this is the initial, this is the terminal, okay? We can find out what that new vector is by taking my last versus my first, my right, like terminal minus the initial, okay? Think of this like your distance formula. If I want to find the distance between 2 points, I subtract my x's, x2 minus x1 squared plus y2 minus y1 squared. Okay, I'm not going to square these because we're working in vectors, but it's the same idea. You start with your second x minus your first x, okay? So if I have an initial point right here, this is my initial point of negative 4, 6, and this is my terminal point over here of 7, negative 2, I'm going to find my vector by taking my initial, the terminal 7 minus my initial negative 4, and that's going to be my horizontal movement, so I put an I on there. And then plus, I'm going to take my -2, that's my vertical movement, minus my 6 where I was at for my j. So I get 11I plus, and I guess I don't need the plus, right? I can just go straight to -8j. There's the vector, that's how much I moved. Okay, let's think about this. I went from -4 to 7. I added 11I. I added 11 on my verticals. I went from 6 to -2. I subtracted 8 on my verticals. Make sense? Okay, so that's how, if you're finding the, combined movement or the vector movement, okay? All right, adding and subtracting vectors. Again, we did this in geometry. We didn't use the same symbols and such like that, but the math involved is the same. When you're adding vectors, you add the horizontal components and you add the vertical components. Or if you're subtracting vectors, you subtract the horizontal components. You subtract the vertical components. That's what you do. You don't mix horizontal and vertical together, so you're careful on that. And then a scalar multiplication says if you have this scalar multiplication on the outside, everything in the vector gets multiplied by that, okay? For my examples, I threw kind of a lot at once because I said I'm going to just do this and get this over with here. So I gave you 3 different vectors, u, v, and w. Okay, so their vectors are given to you. And in the first example, I'm taking -2 times vector v plus 3 times u. So -2 is my scalar. So I have -2 times that vector of v. Well, v was -5i plus 2j. And then 3 times vector u, well, u is 3i minus 4j. All right, scalars, just multiply through. -2 times -5i, I get 10i. -2 times 2j, I get -4j. 3 times 3i, I get 9i. 3 times 4j, I get -12j. I'm going to add in the middle. All right, time to adding those horizontal components. 10i plus 9i, I get 19i. -4j minus 12j, I get -16j. There is my combination of those vectors, okay? What's super nice is when the eyes are on there, it's like terms, and it keeps your horizontals together and your verticals together. All right, my second example here. Notice the double bars. I want the magnitude of w minus u. Well, you can't get the magnitude until you simplify that down into one vector. So the first thing I'm going to do is subtract my w, which needs to come first. That is I minus 7j, minus my u, which is 3i minus 4j. And then I'll take the magnitude. So I minus 3i is -2i. -7j minus a -4j, that becomes plus 4j, which will make it -3j. Now, I have one vector, and now I'm going to take the magnitude. So the magnitude, you think of it as r. It's going to be the square root of my -2 squared plus my -3 squared. We don't include the I and the j in there. It's just the coefficients up. Well, -2 squared is 4. -3 squared is 9. 4 plus 9 is 13. I get the square root of 13. It doesn't simplify down. That's my final answer. Okay? The math involved in this is fairly easy. It's just knowing what the notation is saying to us. Okay? Finding a unit vector that has the same direction as a given non-zero vector. So the rule for this is simply to take your vector and divide by the magnitude of the vector, and you'll be able to find the same unit vector with the same direction, okay? So I have been given vector v, which is 4i minus 2j. So the first thing I'm going to do is find its magnitude. So finding the magnitude, taking the square root of my horizontal component 4 plus the vertical component -2. 4 squared is 16, 2 squared is 4. -2 squared is 4 too. I get the square root of 20, which I can simplify to 2 square root of 5. So there's my magnitude. All right, so my rule says v over the magnitude of v. Okay, and many of these things are on your formula sheet, so you don't have to worry about memorizing them, just know how to use them. So I have 4i, and I'm going to separate them into minus 2j. I'm going to put 4i over 2 square root of 5. I'm going to put 2j over 2 square root of 5 because I'm dividing by that magnitude. It's just math time here. 4 divided by 2, I get 2 over 1. Can't leave a radical, so I multiply by radical on top and bottom. On top, I get 2 radical 5i. On the bottom, radical 5 times radical 5 is the square root of 25, which is 5. On the second one, my 2's cancel. I can't leave a radical in the denominator, so I multiply by radical 5. On top, all that's left is negative radical 5i. On the bottom, square root of 5 times square root of 5 is square root of 25, which equals 5. And I should make sure that's a j and not an I. You can put your j in front of the radical, behind. I'm not super picky. It's funny because I have it written right now as like 2i square root of 5 over 5 minus j square root of 5 over 5. I just need to see them and know that the j and the I are not underneath the square root, okay? Writing a vector in terms of its magnitude and direction. So as you look at this formula, and again, this is given to you on your formula sheet, to write the vector, we do the magnitude times the cosine theta I plus the magnitude times the sine of theta j, which again goes kind of back to the same thing we did on polar coordinates where x gets the cosine theta and y gets the sine theta. Instead of the r that we used to multiply by, we're multiplying by the magnitude, but the same idea. So we're going to write this vector v in terms of I and j when the magnitude is 8 and the directional angle is 210 degrees. So 210 degrees as an ordered pair is, that's my 7 pi over 6, negative radical 3 over 2, and negative 1/2, getting that from my unit circle. So I'm going to do the magnitude, just a minute. I don't know why it does that. Okay, being covered up. There we go. We have the magnitude, which is 8 times the cosine of 210 degrees, and that'll be my I value, plus the magnitude, again, of 8 times the sine of 210 degrees, and that'll be my j value. All right, cosine of 210 is negative radical 3 over 2. Sine of 210 is negative 1/2. 8 times negative radical 3 over 2, I get negative 4 radical 3i. 8 times negative 1/2 is negative 4j. And there is my vector now in terms of I and j. All right, last page. You don't think I can let it go with being completely easy, right? All right. Story problem, right? The magnitude and direction of two forces acting on an object are 70 pounds, south 56 degrees east, got to throw some bearings in here, and 50 pounds at north 72 degrees east, respectively. Okay, so this first one is going to be my first force, or vector 1, and over here, this one's going to be my second force, or vector 2. Find the magnitude to the nearest hundredth of a pound and the directional angle to the nearest tenth of a degree of the resultant force. So both are acting on this object at once. We want the resultant force, and of that force, we want both the directional angle and the magnitude. Okay, so let me get my bearings straight here, okay, and let's start with vector 1. So vector 1 is 70 pounds, and it's going south, so we start south, 56 degrees to the east, and here is my 70 pounds pulling, yanking, I don't know, on some object, okay, 70 pounds. So let's work first with just vector 1 here, and let's figure out what its vector format is, okay? So on my vector 1, I need, and for any vector, I need a magnitude and I need an angle. Okay, so the magnitude is pretty easy right now. The magnitude is 70 pounds. Okay, the angle, and this is something you just have to know the rule. My angle always needs to be from 0, how far around am I? So if you think about this, from 0, I went all the way around to this angle right here. Well, that means I went through 270 degrees plus that 56. So my full angle right here, 270 plus 56, is 326 degrees, okay? So I have to do this angle from 0. And to get it into that fourth quadrant, I need to add that full 270 on. Okay, so for vector 1, when I go to find it, I'm going to do 70 times the cosine of 326 plus, oops, that's going to be my I, plus 70 times the cosine of 326, and that's going to be my J. Okay, plug that into my calculator. Because I'm in degrees, I want to be in degree mode, so 70 times the cosine of 326 gives me a 58.0 I. 70 times the cosine of 326, again, degree mode, negative 39.1 J. Okay, so there's my vector 1 in vector format. So let's go to vector 2. Vector 2 is going 50 pounds, and it's north, 72 degrees to the east, okay? Actually pretty far down, right? So you're like here, vector 2, and this one's only pulling at 50 pounds, okay? All right, so for vector 2, when I go to find my magnitude, it's going to be 50 pounds, I know that. And its angle, it's all about the zero, from the zero, right? So if it's 72 degrees to the east coming that way, 90 minus 72, right? I'm only at 18 degrees. So this one's going to be 18 degrees because it's always from the zero. Okay, you might want to write yourself that. The angle from zero every time. Okay, so vector 2, I'm going to have this magnitude of 50 times the cosine of 18 degrees with my I, plus 50 times this. I did totally mess that up, didn't I, up there? Guys, okay. I'm going to fix it because I don't want to do this. My guess is, now I need to double check myself. This should have been sine, sorry, of 326 degrees J. Let me double check on my calculator, see if I messed that up. 70 sine of 326. Nope, I'm good. Negative 39.1 was the sine, so I'm okay. All right. 50 cosine 18 degrees plus 50 sine of 18 degrees, and that'll be my J. Okay, 50 times the cosine of 18 is about 47.6 I. 50 times the sine of 18 is about 15.5 J. All right, and there is my vector 2. Okay. The angle from zero is probably the key part where most people mess up, so that's definitely where you want to be careful at, okay? Now, so I found my two vectors. Now I want to find, it says the magnitude and the direction of the resultant force, okay? So that's what I need to do next, is find the resultant force. So the resulting force is when they work together. So when V1 plus V2 work together, what do we get? So I'm going to add these two vectors. So when we add, remember, we take our horizontal components of 58.0 plus 47.6, right? That's my I1. And then I take my vertical components of negative 39.1 plus the 15.5. And that's my J. So my resultant ends up being 105.6 I minus 23.6 J. Okay, this is what I'm finding the magnitude of. This is what I'm finding the angle for, okay? So think about 105.6 I minus 23.6 J. So 105.6 is going to come out this way, negative 23.6 J. I'm down here somewhere in my fourth quadrant, right? If you can kind of visualize where that vector is, it goes across 105.6, comes down 23.6. Okay, I'm going to just draw it over here so I have it away from that other picture. It's a little clearer because there's my theta. I'm over 105.6. I'm down 23.6. I'm in my fourth quadrant, right? And I need my R over here. Okay, so I'm going to take the square root. This is for my magnitude of 105.6 squared plus negative 23.6 squared, and take the square root of that. Let my calculator do that. That's a mess. Make sure that negative on the 23.6 is given is inside the parentheses, so it gets squared. Okay, so I have a resultant vector here of about 102.9 pounds, okay? It's not what I had on my paper from the last time I did this, so let me try it one more time. Nope, it's not. I messed up. Okay, let's try that again. How about 108.2? I don't know what I typed in wrong the first time. 108.2 pounds. There's my resultant vector, okay? And then as far as a direction, I need to find that tangent of theta is opposite, which is negative 23.6 divided by 105.6, my adjacent. So remember, I'm going to get my reference angle. I'm not plugging in that negative. Inverse tangent, 23.6 divided by 105.6. My reference angle is 12.6. Okay? Now, this is where we have to think. So 12.6 is this angle in here, okay? Back up to this picture, 12.6. So if I'm going to give a bearing, okay, I'm definitely going south, and then I'm going towards the east. And I need to do 90 minus that 12.6, and it's about 77. Let me see if I probably have more paper and I'm not using it. What do you know? Squeezing this all in here when I don't have to. So I'm going south, I'm going east, and it's 77.4 degrees in there, okay? Now, you also have the option of telling me that it's 347.4 degrees, because that would be from the zero. So you can either use the bearings or you can go from zero. I'll take it either direction, okay? It does say direction angle, so it does like that, the bearing, but I'm okay with the 347.4 since we had to also turn all our bearings into those angles as well, okay? So resultant force, an angle at the end, okay? That's kind of where I'm key at on that one. All right, this is the hardest problem probably on the vectors. They're pretty straightforward, but if you're struggling on them when you're practicing, you need to practice before you tell me you're struggling on them. Page 709, 3 through 72 by 3s. A lot of them go really quickly, but practice some, make sure you're on the right track. And let me know if you have any questions.